There you are. So the next talk will be by, what you see here, Miguel Aragon. He's at College State in New York. He's a visual artist, and he will help us to understand how we can actually look at data through virtual reality. Miguel, take it away.
Well, hi, everybody. Well, first, we'd like to thank for the kind invitation to come to this conference, but at least virtually. I hope next time I can be there in person. So I don't know if somebody in there organizing a team told you, but it would be good if you have a mobile phone. At the end of my talk, I'm going to show some things that you can actually explore interactively. And I want to ask if it could be possible to lower the lights, but I think the lights are already dim, because I'm going to show some dark images. Okay, I'm going to start with my presentation. So I'm an assistant professor at UNAM in Mexico, here in Ensenada, and I'm going to show some work that I've been doing. This is not my regular work. This is something that I like doing on a side. My work is in cosmology and large-scale structure galaxy formation, but I also enjoy doing a lot of visualization and data exploration, public outreach. And sometimes you get some nice surprises from doing that, even though it's not hard science. You get some interesting results. This is work that I've been doing with some, but not directly, but indirectly with some students, with Anarcos, Jose Carvajal, and also some colleagues, Mark Nering and Kai. We show some results on things we did. We all know about virtual reality, and this is being described as the next revolution. Meta, Facebook, is investing a lot of money. Last year, they invested $10 billion on this technology. Even though I don't think the technology is ready yet. My children, for instance, they are not so excited about it. They think it's very cool, but they prefer to go out and play with the ball than choose these things. But we can use it for science. For science, I think this is the right time to start adopting this technology. And I'm going to start talking a little bit first about machine learning. Now that we are in the machine learning session, I will give some soft applications of machine learning, even though I also do some more serious work on this area. I will show you some things that we can do to make pretty images. So I will start with the coma cluster. This is the coma cluster, as seen in the sky. And the coma cluster has like 1,000 galaxies, but you cannot really see the 1,000 galaxies here. You can just see these two galaxies at the center, more or less. What you see is a bunch of stars. So if we could somehow remove those stars and show the galaxies, also increase their size, this is what we will see. So we want to go from here, from using virtual reality just for having fun, to here. Now we can do. We want to do some astronomy, some science in general. So this is the coma cluster again, and the coma cluster, but you only see stars if you look at the sky. But we want to remove them and show the actual galaxies. This is what we get. So like 10 years ago, I made this map based on the Sloan Digital Sky Survey with something like 400,000 galaxies. We use, with so many galaxies, we don't have very good images for all of them. Most of them are just little dots. So we use a template of galaxies of images to place these pretty pictures in the position of the dot. We render this in Blender, and I'm going to show you just a little bit of the animation. So this was but the movie has aged well. You can see here the large-scale structure very clearly, but has the limitation that it is rendered. So you can just see the movie, and that's all you can see. You cannot explore the data. At the time, it was not possible to do this interactively, even in a normal computer, at least not with this many galaxies. So I started working on a new version, and the first thing that I started doing was working on the images. So why do I need to work on images? Because when we constructed this map, we basically have a bunch of dots, which are these galaxies. Most of the galaxies are so far that you only have a few pixels for them. And we want to convert these dots with some properties into fancy images to make our map. This is the template that we use in the original animation. We had 350 galaxies, and we place we found from these 400,000 galaxies which were the galaxies that matched each one of these other galaxies. So the template looks very good, but once you look into the details, you see that the images are actually quite dirty. This was the Sloan survey, and even though it was very good, the resolution was not very high, and then also it was not very deep. So now we have various surveys, like he shows some results from this large survey DESI, which is much deeper. Now, if you go deeper, you also have more objects, and you have foreground, background objects that we have to clean. For the Sloan survey, it was very easy to clean. We just Photoshop, I just cleaned a few images. For DESI, it was much more difficult. So I use a neural network to clean it. So the idea was, I will not show the architecture, but we use something like an autoencoder. We pass a galaxy, and we tell it this is the dirty image, and I'm going to give you the clean image. I had to clean a lot of galaxies by hand on something like Photoshop, and use some techniques. I didn't have much data because I had to clean it by hand. So one dirty trick, literally, that I used was give the neural network dirtier data. So I have the galaxies here with some stars and some background and foreground contamination. So I put even more contamination into the galaxies, and then use the original dirty images as the clean images. So then the neural network learned how to clean these very dirty images. And when I pass normal images, it cleaned them quite well. So this is what we got. I see here the original sample taken from the web interface, and after cleaning the images, I also changed the color scheme. This is the result. So let me show you again. These are the original images with a bunch of background and foreground objects, and this after the neural network. So we did this for like 1,000 galaxies that we have in the new template. So here we see a comparison between the Sloan, DESI, the raw images, and after cleaning with the neural network. And you can see it can remove the objects outside the galaxy and also inside the galaxy. Even these artifacts that you see a lot in DESI are removed very well. So now we have this very nice sample. So now we have to do a matching, because we have hundreds of thousands of galaxies. Most of them are just dots with some properties. And how are you going to match those galaxies, those little dots, to images of galaxies? But for most of them, we cannot, because we just have just dots. But for some galaxies, we can. If we have a little image, if we have a few pixels. So, sorry, the original matching was done in concentration and color. So we just look at the properties of the galaxy, just two properties, how concentrated was the light and the colors of the galaxy. And then we matched that galaxy to the template that we had. But it was not so good. Sometimes it really failed. So now I use something a bit better. So what I did was pass the galaxies through a neural network. And then when you pass the galaxy through a neural network, to a convolutional neural network, you decompose the galaxies. Every layer or every neuron in the network emphasizes some aspects of the image. And that's what you see here. So what you see here are this is the response of the activation of different neurons to this image. So by doing that, we can take these activations and map these activations into a new space. So we can have galaxies enter here. They get mapped into a new space, which has much lower dimensionality. And we can construct these spaces that are low dimensional and more or less semantic. So now here is very easy to find analogs. So I can find a galaxy, and I can find the galaxy that looks like this galaxy in this new map. And this is what we did. So here you see a galaxy, and then the closest galaxies in the template. So it's itself, of course, and then you see the next closest galaxies. This is another example. This is another. I'm working now on inclined galaxies, because this only works for more or less face-on galaxy, which is very limited sample, but it's still good enough. And this is the final template that we have. We have like 1,000 galaxies to produce this map. Now, I'm going to tell you about the actual map. I will not tell the details how it was made, because it's very technical. But I used the Oculus Quest. I will not show it during this talk, because Yesterday, I did a test with Mark Nehring. He had me do some tests, and we saw that the internet was very choppy, so we can't really show it interactively. So we'll be showing some movies. But the Oculus Quest is fully interactive. It's a standalone system, which is really convenient. You don't have to connect it to a computer to visualize, although you can do it if you want to visualize difficult things. It's very cheap. It's like $300, something like that. But it has some limitations. So it's very, very limited hardware. It has a tiny GPU, it has tiny memory, tiny CPU. It also has a heat and battery budget. It's very easy to overheat the thing. It's very easy to drain the battery really fast. So that means that we have to go from hundreds of thousands of galaxies to more or less 80,000 galaxies and 90 frames per second. You also need a very high rate of images, because otherwise your brain cannot, you cannot fool your brain if you show less than 70, 90 frames per second. And you have to do all this in something that is basically a little mobile phone, because that's what it is. The Oculus Quest is just a mobile phone in a nice case. So it is a technical challenge to put all that stuff into one little thing. I will just show you something that I've been doing. Most of it is just playing around, and sometimes there's some science coming from that. So this is a new flight through the universe. And from this, I'm developing already an app. And what you will see here is like the first movie that I show, but this is fully interactive. You can just literally fly around the universe. This is flying around across 80,000 galaxies. I hope with the next versions of Oculus that we have better hardware, so we can put more galaxies. And it is difficult to show you, to convey how amazing this is when you are there, because you are actually there. You see that the voids are really these huge empty areas. You see the filamentary structure of the universe. You see the clusters being connected. It's an experience. Virtual reality is something that you have to experience. You cannot tell people, and you cannot show movies, even though I'm just doing it now. But I encourage you to get a headset, and once I have this app outside, I can send the link around. This gives you a completely new perspective of the large scale structure once you are there, and the difference to some other experiences that require you to be connected to a computer, or that just show dots. Here we are showing in the actual map with more or less actual galaxies. They are matched galaxies. Okay, I'm going to show another example. This is multiplayer, so you can have more than one person in the same map. So that's quite cool, because you can say, oh, let's meet in the Virgo cluster, no? Let's meet in the Pisces Perseus cluster and have a chat there. What you see here, well, these are my two children who were connected, and I'm looking to the map through another computer, and you see the trajectory. So they are flying around. So you can see how they are moving across the map. I don't know if you can see through the video, but there are a bunch of galaxies in this map also. So you see the trajectories, and they are flying through the three-dimensional map. This is so beautiful that I'm already talking to an artist, to a dancer, so we can combine this with some music and create. So do a dancing, but in 3D, not just in the flat surface that we are used to. Once we have a 3D map, but we can interact with the 3D map in a more natural way than if we do it in a computer, because in the computer we only have the projection, or we can use 3D glasses and it's still there, but you cannot really touch the stuff, and it is quite cumbersome to interact. But if we have a real 3D map, then it is very easy to do anything 3D. And I'm going to show you a little example. This is again this map, and what you see in red is the zone of avoidance. And this is for a little video that I'm making, a little visualization project. So I'm putting galaxies in the zone of avoidance by hand. So it doesn't have to be really scientific. I just want it to look pretty. So just to show you how I can do this, I'm just making a little region of interest with my hands, or with the controller, but you can use also your hands. In the same way, you can pick galaxies, and you can do anything you want here, and you can select them And you notice also the galaxies are the actual galaxies. These are not just little dots. Everything is running in real time on the Oculus Quest. So although there are systems that already do something like this, and some even much better things like that, as far as I know, these systems are require you to have very good hardware on your computer and connect the hardware to connect your Oculus to the hardware. What I'm trying to do is to have everything standalone, because not everybody has access to these machines or wants to connect these machines. Sometimes you just want to use your headset and put it on. I was commenting at the beginning that my children are not so they are not so convinced about this. They like the headsets, but they still prefer to go outside. And I think part of the reason is because this is an extra layer that you put. No, you cannot just start interacting in 3D. You have to put something that is heavy, and then if you have to, the more you add, the more layers you add to the interaction, the more difficult it becomes. So it doesn't feel so natural anymore. I'm going to talk a little bit about this is a project that I was invited by Kai, Mark, 2 years ago in a conference in South Africa. I was showing some of these animations to Mark, and then Mark said, "Oh, look, this we are working on something like that. So why don't you join?" And but what the paper was about is about the twisting of matter around filaments. And I'm showing here one example where you can see the filament here, and you see the matter not twisting around it. This takes some time. You have to look around. Sorry, in 3D. The 3D map and find the right projection. This is another example of a nice filament that took a while to find. So you had to move around in 3D and kind of find it, and then turn it, align it to the screen. So it's not a very natural process the way you will do it normally. But if you do it in virtual reality, then you can just move around the map. So you are in the map. It's like you move around a tree. So you are in the tree and you look around the branches in the tree. Here is the same with the cosmic web. So you are in this cosmic web in this network, and you just look around the network. You just move around, and you can focus on one little area. Here you can see, for instance, a wall that we just cross a wall here at the center of the screen. In 2D, you will have to find the right projection. In 3D, you just see a wall in front of you. It's very clear that there is a wall there. So you want to find structures in the data. This is the natural way to do it, much easier. It removes one layer. No? It removes the layer of projecting from 3D to 2D on the screen. Okay, see, I have good time. So another little thing that I've been playing around is this. We are all used to seeing these density fields, and sometimes we make the analogy of a density field like a landscape. Even I've done this with Rin and Bernard. As this analogy, we have used this analogy as an actual tool to, in this case, to find the riches, the filaments and the walls in the density distribution. So we can go beyond just analogy and do the actual thing. So what I'm going to show you is I converted this density field into an actual landscape where the clusters are the high peaks and the voids are the low valleys. So when you have a landscape, you can walk around the landscape. I'm just going to go a bit further. So you can walk around the landscape and walk through the ridges. Here we are passing through a little filament. This is probably a wall in 3D. You can see in these dark regions the voids. And when I was preparing my talk, I realized that I have never walked inside a void, actually. It just doesn't feel right to walk inside a void. So these are kind of shallow voids. Now we are crossing in between. Well, this is a quite highly dense region. I'm going behind a little bit, because there you can see also some void in clouds. Sometimes you see a little hill, and then on top of the hill, there is a little void there. Now we are going through a filament, and then on the right, we have a deep void. I haven't found an application for this yet, but this is a lot of fun. It's really, really fun to move around this map. And I want to use this also for outreach. Oh, I have used it already for outreach, actually. Okay, now I want to show you some interactive experiments that I've been doing. And I'm using WebXR, which is the new web technology. It's a bit more limited than what I showed you before, but I think it has more potential at the moment. The interactions that I showed you before were made in Unity. And Unity and other virtual reality pipelines are very, very complex to use. This is just the interface of the Unity editor, and there is a lot of stuff that you have to learn apart from just programming. It's not so difficult, just C#, but then you have all these things on top. So it took me like 6 months to go from 0 to produce something more or less decent, and it took me like a year to produce the interaction that I show you. So that is just too much time. I do this because I like it, but there are other options now. They are more limited, but we are getting there. So I think this will bring a democratization of virtual reality. So you don't need to be an expert on these systems or to have a studio working with you, but you can use much simpler tools like a frame, a Babylon, a tree. Yes, I will be using a frame. So the first example is from some work that I'm doing on the hierarchical deconstruction of voids. So you see here density field and a void, and then you see the void, and you see here also the subvoids, and you see the walls that make the membrane of this void, and then you see the subwalls that make the membranes of the subvoids inside this large void. You see the filaments here, the filaments around the void, in the membrane of the void, and then you see also the filaments inside of the intravoid filaments. Now this is impossible to show on a projection. But we can do it in 3D. So now if you get your phones, in principle, you can just point to the screen. So I'm going to do it. So if I point to the screen, let me go out 1 second, please. So you point to the screen, you can just go to the link. And I'm going to show you, I will not show it on my phone, but you just give allow. It's going to ask you, you give permission to use the position of the phone and the orientation, and then you can see, and you can move around this little map. So with this, you can just explore it. You can look in any direction. You can also, but not right now, but then later you can walk around the model and see it from outside and from any angle. So what you see here, I will just show you in the computer. What you see here are the filaments inside the void. And again, even though this is a bit better than, well, it's a lot better than just showing the 2D projection. But you look in the phone, then you're actually there. You can also put this in a cool cardboard and see it in actual 3D, again with the right orientation and everything. So this is much easier to show the structure inside the voids in this case. And you can see now the individual filaments. You can focus on one of them and see the connections between different filaments. You can just explore the data. This is much easier to program also. This is just HTML and a little bit of JavaScript. It really takes just a couple of hours to understand how this works and how to implement it. So you can go from 6 months to 1 evening and have something that is not so fancy, but it's still very useful. So I really would like you to check it. So I don't know if people try it and it worked. Would it be possible to have some feedback?
It works.
It works. Okay. Oh, great. The link is also here. Well, I will give the presentation later if you want to check it. Okay, I'm going to show you another example. This is a map of galaxies, and here let me just go again just to make sure that everything is working well. Okay, again, you just click and it will send you to the map. Okay. And here, what we have here is a map of halos from a simulation. And just to show you here a little more information, I show the connectivity between the halos with something very simple. This is just the minimum spanning trees of the halos. But again, this one is a bit different. In this one, you can move around by touching your screen. So let me show you. So if you touch your screen, you move in that direction. So you just point to where you want to go, and you touch the screen and you move around. So that's how you can actually fly on this one. The other one you cannot fly. You can just walk around. And this one you can walk around and you can fly. And because this is a virtual space, this is like an object placed in your room, so you can move around it with you got your camera, and this becomes a window. Your phone becomes a virtual window that lets you see this virtual object in this physical space. So that's also very cool. It makes visualization in interaction with data much more natural than just seeing it on the screen, because you can move around it and focus on one little part. And again, you can also put this on a Google Cardboard and see it in 3D. So again, you see here all the connections, but this is something very simple, just the minimum spanning tree. But you can do much complex things, like showing the filaments, or in 3D, you can also show the walls or anything you want. And again, this is the programming for this is very simple. Let me see, I lost my here. And finally, I have a map of the local universe. Okay, let me go here. This is for a project that I'm building with some students. We are making a map of the local universe, of all the local universe, the most important structures. I don't know if you are familiar with Atlas of the Universe. It's a very nice, very old website. We want to do like an Atlas of the Universe, but in 3D, that you can just go to any region and explore it in 3D. So this is a map of the local universe. I think it's up to like 20 or 30 megaparsec. And here you see the Milky Way and Andromeda, the Triangulum. The first line is 1 megaparsec, then you have 5 megaparsecs and 10 megaparsecs. Here in purple, you see the local void. So I'm going to get inside the local void. Again, you don't have to look at my presentation. You better explore with your phones. But this big bubble here is the local void. So you can go to the local void and see from inside the local void down into the local sheet. So there we see here our galaxy. Now, if I go back to the local sheet through the void, then if you look around with your phone, you see that the local void is void, it is empty. So you're in this huge bubble with nothing inside. So I go back to the local sheet. Then from the local sheet, we can see some groups, the Virgo cluster. Then you can also have a much better idea of how close or how far are these structures and where they are located in 3D. Even I work on this and I see maps all the time, but even then it is difficult sometimes to get an idea and know where is everything. I see the maps and I keep having to stop and think, okay, where is the Virgo cluster? Not located to the local supercluster, to the plane of the local sheet. But once you interact with this, it's a lot easier to understand. So again, you can also fly on this one. I didn't mention it, but you can also fly by just touching the screen, and you move in that direction. To show you. Thank you very much for your attention. And I don't know if there are any questions or comments.
Thank you. That was really amazing to see. It's very inspiring. I was wondering if you also got some new insights into data sets by visualizing it in 3D and seeing some new correlations that would have been difficult to see in 2D, for example.
Yes, actually in this, I don't know what to do about this, the structure that we see here. This is something that I have talked with Mark, and we only saw it once. You only see once you get into the helmet. but now we know it's there. No, but in 3D, it's very easy to miss these little regions that are like vortexes. So at this point, we haven't done much with that because I think it's probably something artificial. Maybe it's an artifact of the data, of the way I'm visualizing these objects. Let me go back. But yes, something you can just see, or no, you cannot just see, but some things are easier to see once you are there, like the twisting of the filaments. I have seen this animation before in 3D when you see it on the screen, but it's just there. But somehow when you are there, things just become more real in a sense. I don't know how to explain it. Mark has been also working with virtual reality for a while, and it's really different. It's the same as when you print something in 3D. I also play with that, with 3D printing. Once you hold something in a model in your hands, the